All right, so we're going to look at limits, which you may have been introduced to before. And what we're going to do...
Wait a minute, wait.
Up at the front. Okay. We're going to look at infinitesimal changes. Right, so there's a word for you, which calculus is actually built on.
Limits.
Well, yes, limits, but there's two parts of it, which is really small changes. All of the proofs in calculus, which I will tell you about but not really use, okay, are built on really small changes. Really, really small. Okay? And we're going to use that information to predict and evaluate limit statements. Okay? So we're going to look at the notation, the limit, and we'll translate it. Okay, so that's your limit statement. And we're going to write this sentence as x approaches. It means it's not necessarily equal to it, but as x approaches a. The y value of f of x, usually f of x is a graph or an equation, approaches L. Notice that none of those things say equal to. Just approaching. Getting close to. Getting really, really close to. Okay? So y can equal L, but does not have to. Right? They can be equal, but they don't have to be equal. Same thing with x. X can equal a, but it doesn't have to. The idea behind the limit is that you just get really, really close to it and you predict what value would be there. Okay, so we're going to start with real context and then we'll get into some of the algebra. Consider a spring that will break only when a weight of 10 pounds or more is attached. How far can the spring stretch? Okay, so weight of 0, weight of 3, weight of 7.5, weight of 9.5, weight of 9.999. The limit as the weight approaches what? Okay, what's the weight approaching? 10 pounds, right? Maximum of 10 pounds. Equals S. They labeled it right here. Whatever that length of the spring is. Okay, so write the sentence that describes that limit statement using the real words as the weight approaches 10 pounds. Right? Not equal to 10 pounds because then it would break. As the weight approaches 10 pounds, the length of the spring approaches I don't know how long it is, and I don't know what units they're measuring it in. Yes? Yeah, sure. Okay, so notice that neither of these say equal, and in this particular case, you don't want to equal 10 pounds. It would break. You want to be just below 10 pounds. Okay, see if you can draw a graph and write a limit statement for number 2. Consider that you're entering the highway from an on-ramp. Usually you're going slower on the on-ramp before you get onto the highway. What speed are you approaching as you continue driving on the highway? Draw a graph, write a limit statement. Let's call this time. Let's call this speed. Let's say that t equals 0. Start on the on-ramp. Okay? Just so we all have a similar starting point. Then write your own limit statement. And then you can try number 3 where you write it based on your own information. Make it reasonable. Make sure that your statement is actually reasonable. Okay? Maybe write your limit statement before you draw the graph. What do you think your speed is doing as you get from the on-ramp onto the highway? Yep, your speed is going up. But does your speed approach any certain number? Okay, what should your speed approach? How about that? Depending upon which state you're driving on the highway in, could be a different number. So, okay, this is an X number. How do you know?
So we're doing a number?
Yeah, pick a number, right? You pick a number. Like, how long does it take you to get on the on-ramp?
So we're picking a time?
Yeah. Well, okay, how long does it take you to get on the on-ramp? When are you actually on the highway? Like, put some units to this. How long do you think it's going to take you? 2 minutes? 5 minutes? I guess it depends.
Oh, yeah. Onto the highway. But it's approaching it. Big traffic. I don't know, I can't.
Yeah,
It's
going
going
fast. Like, do they need it?
That means that like traffic
Yes.
crash.
Yeah.
Right? You pick numbers that seem reasonable.
Okay.
You pick the time.
Yeah. How long do you think it's going to take? How long before your speed approaches whatever number you think it's going to approach?
Well, it depends on the car.
It does. Well, it probably depends more on the location and time of day. But, okay. So, here we go. I'm going to start my graph here because I'm going to assume that I'm not stopped before I get on the on-ramp. Okay, the limit, eyes up, t approaches something. I'm going to name my graph f of x. You can name it anything you want. Okay, notice that the limit statement is 2 different rows. They're like small rows, top row, bottom row, same size as f of x. Okay, equals. Well, my speed is probably going to increase as I get on the highway. And then let's just assume the traffic's not too terrible. Eventually your speed should level out. Okay, now I don't have any numbers on this, but I should probably put some times on it. Maybe it takes me a minute to get on the on-ramp. Maybe it's half a minute. Guys, it's not important. You just have to put some sort of scale to it that might be reasonable. So we'll go half a minute. Okay? All right. So let's say that it's still kind of slow, you're merging, you're getting onto the highway, maybe, 1, 2, 2, as T approaches 2 minutes. 2 minutes to get on the highway. My speed approaches 55, 60? I don't know. It depends. Okay? But look at where the X values go. Look at where the Y values go. Are you going 55? Maybe. Maybe you're just getting closer to 55. Right? Closer to. Maybe equal, maybe not. But the equals is not important. All this means is that you're approaching. I know that you see an equal sign here. It is approaching because you're doing a limit statement. As time approaches 2 minutes, speed approaches 55, we'll say, miles per hour. This is your X coordinate. This is your Y coordinate. So in this particular graph, this is the spot I'm looking at, right? For the graph that I drew. Okay. Notice that it's matching up the X coordinate and the Y coordinate. Maybe it's equal, maybe it's not. Okay, write your own statement. You can use data that you did for your project, or you can make up an information. Okay? Sketch what you think the picture is, write a limit statement. We will have to share some of them. Okay. Write your own limit statement with units and quantities that make sense. Okay. It could be based off of the data you collected. You could create something new if you want. It doesn't have to, but it can. There's only certain situations. Like, think of
As I get older, you're approaching like a sprint. You're approaching supermills, but not quite. Right? That you can still be better.
it just doesn't have to.
I had O7.
Okay, anybody ready to share? For Candy, who wants to share their statement? We have chocolate, little bite size, and Starburst. Who wants to share their statement? Yes, Sammy.
I said as the time approaches 10 minutes, the heat of the oven approaches 350 degrees. 'Cause it's like reheating the oven.
That is great. Okay, so as T, I'm just going to say approaches 10 minutes, oven temp approaches 350. Yeah, and it might actually equal, but it, right, not quite. You can come choose Candy for sharing. Okay, any other statements? Sean?
Once at the time approaches 2017, money spent on pets approaches $69.4 billion.
Okay, say it again, because I can't. No.
At the time approaches 2017, the money spent on pets approaches $69.4 billion.
Okay, yeah, so as the year approaches 2017, as we are getting closer to 2017, the amount of money spent is approaching 69.4 billion, which could very easily be a point on the graph, right? But you're on your way there. Come and choose. Kelly, you had your hand up.
Yeah.
Okay.
As the year approaches 2019, life expectancy in Cambodia approaches 65 years.
Okay, there you go. As the year approaches, so I could change that T to Y, it doesn't matter. As the year approaches 2019, the life expectancy approaches 65. Yes, very nice. Come choose. Okay, so your limit statements can represent real situations. Think of part 3 of your project might be to evaluate and explain certain limit statements that are connected to the data. Okay, so now that we have a little bit of intro there, we're actually going to look at some of the notation. Okay, so this time I drew the graphs for you. Right? Have the graphs. They might be a little hard to see, but I'm just going to bold mine here. Okay? Just so I can see it a little better. And we're going to answer the questions graphically, right? Our first topic is limits graphically. So we're going to read the points off the graph. Now, this little negative here means from the left. Right? That little negative means from the left. The limit as x approaches 1. So I'm just going to put a dot on the graph at 1. Because that's the spot on the graph I'm looking at. The limit as x approaches 1 from the left. Okay? So from the left looks like this. What's the y value that it's pointing at? 2. Okay? And I'm going to say the limit, this one means from the right side, as you draw an arrow towards the x value of 1, what is the y value that you're pointing at? 2. Now, if these things are pointing in the same direction, when you don't see a superscript here, that implies left and right. And right. And in this particular graph, that's actually a point on the graph. Right. We're starting out with really simple pictures. They'll get more complicated. The idea is that you can connect the x and the y coordinates. You can work forwards, you can work backwards. Okay, this time there's actually an open point on the graph. Okay, from the left means I'm going to start on the left side of the graph and I'm going to draw towards, what is the y value you're pointing at, right? Approaching. No, what y value are you pointing at? Not what's there. 2. It's not equals. It's what are you pointing at when you get there, regardless of what's actually there. Okay, so if I go from the right, this is why limits get tricky, is because it doesn't matter where the points are, it matters what you're pointing at. It matters what I'm tracing as I get there. Okay, so as I trace from the right, still pointing at 2. The first 2 statements is the third statement written as 1. When you don't see a superscript, that means left and right. Means I have to compare, make sure we're pointing in the same direction. In this particular case, what Michael said is correct. There is no point there. F of 1 does not exist. But notice the point doesn't affect the limit statement. Okay. Third graph. I'm going to highlight. You answer the questions. Okay. Okay. Let's go. Naomi. First answer block. 2. Katie, second one. Rania, third one. Yes. Christina, last one. Not 2. Where's the actual point? No, look at the graph. 4. Yeah, notice that the first 3 statements are connected. The last one has nothing to do with the limit statement. Okay. Ooh, last one on this row. Okay, I'm going to highlight. You answer. Okay. And I'm just drawing the open circles and the dots bigger because I printed kind of small. Okay. Okay, here we go. Who wants to answer first row? Limit from the left. Yes, Sean. 2. Agreed. Alex, from the right? Maybe. 4. Sure, you can have a piece. All right, last one. Oh, okay. So when I see no superscript, that means left and right. Is 2 equal to 4? No, that means doesn't exist. If they don't point in the same place, it does not exist. Right? All of the rest of these, the arrows met in the middle. That's why that third limit statement worked. This one doesn't work because they don't point in the same place. Okay, f of 1. It does. See the closed point? Hiding up there. I know, the point's plotted really small. Okay. Next row. We get a little trickier. Now I've got asymptotes in my graph. Okay, so I'm going to just draw a little dotted line on here for my asymptotes are so that you can see them. Okay. So right here, we have a vertical asymptote at x equals 2. And we also have a horizontal at y equals 2. Just in case you couldn't tell exactly where they were. All right. We'll go. Okay. All right. First row. As x approaches 2 from the left, raise your hand. What do you think, Kelly? Infinity, yes. Would you like a chocolate or a Starburst? Ha. Okay, second row, 2 from the right. Ethan? It is still infinity. Would you like a chocolate or a Starburst? There you go. There you go. Okay. Ooh. As x approaches 2, notice that that third statement is the first 2 combined. So what would it be? Just infinity. Right? Points up. Okay. F of 2. Ben?
Does not exist.
Yes. Starburst or chocolate? No, one or the other. Snickers. All right. Okay, next row. You have asymptotes. Right here, you have a vertical at x equals positive 2. You have a horizontal asymptote at y equals 2. Okay. First one. 2 from the left is negative infinity. Okay. 2 from the right, positive infinity. Notice that the first 2 statements don't match. Does not exist. I'm going to put / undefined here. Okay, f of 2. There is no point. Yeah, it does not exist, undefined. They're kind of interchangeable. I won't make you pick between the two. There's small differences between them. Okay. So this graph is a little bit hard to see, so I'm going to zoom in because it's hard to read this one. So I'm going to redraw that section right here. All I'm doing is I'm zooming in so that you can see what's happening. Okay. Oh, there you go. So I zoomed in. That's really what the picture looks like. And this actually should say 0. Not 2, sorry. Okay. Don't yell out the answer. If you yell it, no one gets candy. Okay. So we'll do candy for these 4. Raise your hand. This is the picture. The limit as x approaches 0 from the left. Yes? It is 0. Okay. Starburst or chocolate? Yeah, you can come get it. Okay, yes? 0. Sam, last one? 0. Yes? Okay. Last one? Do you want chocolate or Starburst?
I'll take Starburst.
Starburst, here you go. You can come grab one. Okay. Okay. Back here. 0. Yes, I'm going to put question mark because, like, it's really... No, I'm going to go with 0, yes. But, depending upon the equation that gives you this, it gets a little funny sometimes. This is an oscillating graph. Ooh, okay. To divide, sometimes the graph converges to 0, which is why my limit statements actually worked. Sometimes they don't converge. Think about your sine graphs. They just keep going up and down, no converging. Right? This particular one happens to converge. All right. Another 30 seconds. Answer your questions. Only half of these have candy predetermined by which ones. So you don't know until after you answer it. But I'm picking which ones get candy now. I've decided. Okay, decided. All right, answer to number 1. The limit as x approaches -2. Yes. Is 3, correct. That one did not have candy, though. All right, the second one. The x approaches 1 from the left. 1 from the left is 1. That was candy. Come pick. Okay. Okay. All right, third one. -1. 1 from the right is -1. That one was candy. Come pick. Okay. Fourth one.
Does not exist.
Does not exist. That one was not candy. Okay. F of 1. -1. Yes, that one was candy. Okay. Top right. The limit as x approaches 4. It is infinity. That was candy. Come pick. Okay, there's only one more candy left. Okay. Alex?
0.
Yes, that was not candy, though. Sorry, it was not. Okay. This one?
This is breezy.
All right, Ethan, go for it.
0.
Nope.
1.
Hold on. No, you only get one guess.
Oh,
Anybody who hasn't answered yet want to try? Who hasn't answered?
I meant it twice.
Nobody else wants to give this one a try as x approaches negative infinity? Shh, hold on. Yes. 1. That one was Candy. Okay. Yeah, guys, it's possible to have 2 horizontal asymptotes. I know that you might not believe that, but it is possible.
But how do you know that that's
Because I labeled it. Right, I labeled the asymptotes because they're not on the graph. Otherwise, I would draw the dotted line so you could see that. Okay, the limit as x approaches 7. 3. Not 3. It's 1. Okay, so as you trace the graph from the left and as you trace the graph from the right, you are pointing at 1. The limit is 1. Michael, tell me what the point is. No. Where's the point? 3. Okay, so make sure you get them in the right place. All right, guys, that was limits graphically. Check it off. Okay, table. This is where you're going to need your calculator. All right. Okay. You may or may not know what that graph looks like, but it doesn't matter. Okay. Now, there are 2 ways to do this. Plug it in and figure out what the y coordinate is. Okay? Now, you can type this in y equals. You can look at the table. It's actually probably faster to do this on the home screen. So, what we're going to do is you are going to store the value for x. X store 0.9. The reason I think it's faster this way is because there's less setup. Okay? Because I want x to be 0.9. So here are your buttons. You type your x, which is here. Your store button is down here between the 1 and the 4. Oh, sorry, thank you. 0.9, store x. Sorry, enter. There you go. Okay. Now, I'm going to type in this statement. X squared minus 1. Don't forget your parentheses. X minus 1. Enter. Oh, 1.9. It's a really fast way to evaluate without having to deal with the y equals and the table formatting. Now, the nice thing is once you type it once, you are just scrolling up and re-highlighting, so you don't have to keep typing it. You just have to pick your next value for x. Right? If you don't have an 84 that does this, just borrow one from me. So 1.99. It's a lot faster than trying to format the table and do it there. Okay. 0.999. Store for x. This is also a really good tool for checking answers, SATs, things like that. Okay. All right. 1.999. Okay. But I don't want you to fill out this. Nope, don't do that one. Leave it out. Don't care what goes there. Do the other side. Okay. Keep going. This is a really fast way to evaluate a function without having to actually type in the numbers. Okay. So now that I'm looking at my table, right? This time I'm not looking at a graph. I'm looking at a table. As x approaches 1 from the left. Which side of the table is that? To the left of 1. That's here. Okay. So I'm doing that. What is the y value getting close to? 2. That means that the limit is 2. Notice you don't have to have a graph to answer a limit statement. You can do it with the table. But notice that I'm actually getting closer to 1. Okay? 1 from the right. I'm going to put question mark because I didn't fill out that square. Is also 2. Remember that that third statement is just the first two put together. It doesn't actually matter what the point is. All that it matters is that the limits are equal. Okay. Try B. Yep, absolute value. Okay, that's fine. We can do it. Your absolute value is math num ABS. Okay, that's where your absolute value symbols are. Math number ABS. Okay, x minus 1 divide x minus 1. Unless you remember how to rewrite that as a piecewise. Okay, so 0.9 store for x. Let's try this again. Okay. Oh, I just get -1. Okay. Oh, still -1. Ooh, still -1. Again, don't fill out that middle row there, that middle one. Notice you might get undefined anyways, right? All of those things I made dividing by 0, which you can't evaluate. Okay, try the other side. Huh. Looking at my table, math num ABS. Math, arrow over in a number. Okay, you get -1, 1 does not exist. All right, last two. Okay, this really means x less than 1, x more than 1. That's what not equal to 1 means. Less than 1 and more than 1. Piecewise definition, which is why we go over that. You have to figure out which one of these things is the left side and which one of these things is the right side. Well, this means the left. Right? Less than 1 is to the left of 1. This one means the right. That way, when you are looking at the limit statement, you know which piece to look at in the piecewise definition. Which means I'm only looking at the first row. Well, I can evaluate that one by hand. 0.9, 0.99, 0.999. Right? Because this happens to be the left and the right side. Left and right means I'm only looking at this part right here. This is the left. This is the right. Notice how those values correspond to those inequalities. You have to pick out the correct portion. Right? I'm still evaluating here. I'm plugging it in. Okay. On the left, we are approaching the y value of 1. On the right, I am approaching the y value of 1, which means that the limit is 1. but you're doing it by just looking at the y coordinates. Could you try to sketch a picture to help you? Sure, you could do that. Okay, let's do our last piecewise. You got left and right. You have to figure out which one is the left, which one is the right. To the left of 1. That means less than 1. So this is the left side. To the right of 1 is this one. Okay, now that I have the two parts decided, okay, I'm actually going to evaluate. So the left is this right here. Those are the numbers I'm going to plug in to the green portion. 0.9 store for x. 2x minus 4. Okay, 0.99 store for x. 2x minus 4. Oh, negative 2 point. Okay, can do that. 0.999 store for x. Okay. I'm pretty certain, I feel confident saying negative 2. It looks like on the left, the numbers are getting closer to negative 2. Notice it's the y coordinate. Okay, now I'm going to do the right side. Okay, 1.001 store for x. Okay, except on the right, I have to use the x squared plus 3. 4.002. Okay, 1.01 store for x. 4.02. 1.1. Okay, 4.21. It looks like as I am approaching 1 from the right, the y values are getting closer to 4, which means that this limit does not exist because they're not the same. But notice I didn't look at the graph, right? You can do them graphically, you can do them in a table. A little bit of a strategy. I boxed up my limit statements. The first 4 all deal with the x coordinate of negative 1. So I see this. I see a point, and so there are no choices on points. They have to be on the graph. Everything else can be open circles. So right here, look at that. Open circle. Negative 1, 0 from the left. This way. Okay? Doesn't really matter what else happens. Negative 1 from the right. Okay? Check, check, check. As all I'm doing is putting little placeholders. You connect it as you see fit. At 1, okay? 1 from, okay, well 1, 0 I see as a point. Okay, check. 1 from the left is 4. Limits can be open points. The only thing you actually have to plot are actual coordinates. 1 from the right is negative 2. This is it, guys. When I grade a limit graph, that's what I'm going to grade, is this right here. Other than this, you connect the dots. Those are all the limit statements right there. My little tails, that's from the left side or the right side. Then you connect. But let's try to make it a function so passes the vertical line test. Let's connect the dots. Generally, anything that looks like that, but the bold parts, that's the part that makes the limit statements true. Right? The little tail is for the left and for the right. For the left and for the right. And then you've got points.